Good afternoon, everyone. Thank you for joining us today. This is the scheduled webinar today with Dr. Yongtao Guan. And the presentation of the talk is the Group Network Hawks process. Dr. Guan is a professor of management science at the Miami Herbert Business School at the University of Miami. Prior to joining the University of Miami in 2011, he was an assistant and associate professor of biostatistics at Yale University from 2006 to 2011, and also an assistant professor of management science at the University of Miami from 2003 through 2006. He was the chair of Management Science Department from 2013 to 2020, and the director of the Deloitte Institute for Research and Practice in Analytics from 2018 to 2021, both at the University of Miami, and also the professor of Information Systems at the Chinese University of Hong Kong in Shenzhen through 2022. He specializes in modeling spatial, temporal, and spatial-temporal data that commonly arise in business, environmental, medical, and social media applications. He received his PhD in 2003 under the advisor of James Calvin and Michael Sherman, and he's also a recipient of the H.O. Hartley Award in 2015. So welcome, Dr. Guan and participants. Again, the presentation title is Group Network Hawks Process. Dr. Guan, please take it away.
Hey, thank you, Marcy, for the introduction, and thanks, Elaine, Marcy, for the invitation. So today I'm going to share some recent work on point processes, and this is joint work with Haochen Xu, Gangang Xu, and Gangang actually he was also a former student of the same department, and also with the Guanhua Fang and Xuening Zhu. So here's the outline for the talk today. So firstly, I wanted to talk about the motivating data example, and then and we can talk about the proposed model, and finally is a quick summary for the talk. Okay, so first the motivating example. So the kind of data we analyze here are point processes, and the application we're considering are posting times of social media users. And in our application, we collect data of over 2,000 Sina Weibo users for a 15-day period. And what you see on this slide is a typical post that you would see. Okay, so there are some contents in the post, just like Twitter. And then there's also the blog that you see, and that corresponding to, that gives you the time as to when the post was made. So you think about social media data, then there are certainly also the social network structure that will not only the posting times with the made by each user for the post they made, but also there's a social network structure among the users. Okay, so how do we characterize the network structure? Okay, so let's consider a network of M users. They may have posting time, you know, at each one has a set of posting time stamps. So the network structure is represented by adjacency matrix. So the capital A is the matrix. We go inside the entry, the ij entry. If you look at it, for example, the left, the rows corresponding to 4 users, the column corresponding to 4 users. If user 1 and user 2, they are connected in a way, to be more specific, if user 1 follow user 2, then we say the Aij is equal to 1. If on the other hand, if you see the 4th user, she did not have any connection with the user 2, then you will see this part is empty. So we simply set Aij to be equal to 0. And then all the diagonal elements are set to be equal to 0. So the user a given user just does not follow him or herself. So based on the adjacency matrix, we can define the so-called ith degree for the user I, and also the in degree for user I. So ith degree basically gives you the number of users user I follows, And the in degree, simply say, is the number of users that follow user I. So for our data set, we add up all the AIJ components in the adjacency matrix and divide by m times m minus 1. Basically, that's all the possible pairs, possible non-zero values in the adjacency matrix. And so that gives the 2.0. So meaning that, so on average, users follow about 2.7% of the users in the data. And this is a, kind of sparse as we expected for this from this kind of data. Okay, so we have done some preliminary analysis for the data set. So what you see on the slides are 4 plots. The first one gives you the user accounts. So basically look at this 15-day period for each user. We look at how many posts the user has made. And then we plot the histogram. So apparently, this is very highly skewed. Most of the users are not really so active, but there are some users that post, let's say, around 600 posts in this 15-day period. That's like 40 posts per day. So there are some highly active users in the group, but the majority are not really that so active. The second, the top right plot, what you see here is the intensity plot of the activities. We basically combining all the users, and we try to see what are the patterns during this time period. We look at it from, this is 1, 2, 3, 4, 5. This is a 5-day period of time. So we estimate the intensity functions. Intensity function basically describe how likely for an event to happen at a given time point. So what we see is a clear daily pattern of the intensity function. If you think about human behaviors, this is something really common, right? So at least one thing we can see, if at night there's not going to be much activities, so you're going to see some dip here, right? During the day, at a certain time of the day, people may tend to be more active than at other times. And so that therefore you would see some peaks. Nevertheless, you would see the fluctuations throughout the day, and the daily pattern actually repeats, across the different days. So this is something that we need to keep in mind when we try to analyze the data. So the bottom left plot gives us the gap time between the distance. So basically the gap time between the posting times of 2 adjacent posts from the same user. Okay, so basically I look at it, if a user let's the first user, he made a point at this particular time, and then I look back, try to see when did he or she made the post right before those flat, and then calculate the distance between them. That's the gap time. Okay, so the gap time is clearly highly skewed to the right. And this is really something we would anticipate to see because you think about gap time, and typically, for example, you think about it, that can be derived from Poisson process, homogeneous Poisson process, let's say. The gap time is going to follow exponential distribution. So exponential distribution will be skewed to the right. But the question actually is, well, would something as simple as exponential distribution be adequate? Right? In our experience, typically, no, it's not. Maybe there are some more complicated patterns, let's say, for example, clustered patterns. And that tend to make sense because, think about human activities. Again, you use social media, you tend to use in a concentrated time period, and then you leave and then come back again after some time and then do this again, right? So these events will arrive in clusters naturally, as the nature of human behaviors. So that's something that we may want to ask, is there any cluster or not, right? So the last plot still plots the gap time, but they plot 2 kinds of gap time. On the x-axis is plots the gap time of between a user's post and a post from his or her friends. So basically, if the first user make a post at a given particular time point, and then we look back among his or her friends, right? Look at all the posts made by his or her friend before this time point. We pick the one that is closest to the user I's given post and calculate the distance between them. So that's the gap time between user I and his or her friend. On the y-axis, that plots the quantiles of the gap time for the user I and his non-friends. So just like we can calculate the gap time between user and his or her friends, we can also look at the posts made by those who are not his or her friends, right? And we can also calculate the gap time between the user's posting time and the most adjacent posting time from his non-friends. Of course, we want to compare in a way that is that is fair, because the number of friends a person has and the number of non-friends the person has in the same network may be greatly different from each other. So what we did is really we put them, to be the same. We typically there are no non-friends than there are more non-friends than friends. So we, given the number of friends the person has, we sample, the same number of non-friends from all the possible non-friends in order to calculate the gap time between the person, the user, and his or her non-friends. Okay, so basically what we are seeing here are we're plotting comparing the quantiles of gap time non-friends versus friends. So x-axis is for friends and y-axis is for non-friends. So what we can see is the gap time for non-friends. Okay, so this is above this this line 45 degree direction line. So this tells me the quantile for gap time for between non-friends is larger than that between friends. Okay, so what that tells me, what that says is implies is the behavior of a user is likely affected by the behavior of his friends. Compared to, of course, he's not going to be affected by the behavior of his non-friends because they are not connected with each other. Okay, so nevertheless, the message that we see from the plots, from all the 4 plots, are there's a great heterogeneity in terms of the activity level. There's for a given day, there's a heterogeneity within the day in terms of how active a user might be. And there might be clustered patterns, but that's something we yet to be seen, or at least to be investigated. And lastly, there's evidence that a person's behavior, a user's behavior, is affected by the activity patterns of the friend that he or she is connected to. And we also look at, we define it, when we look at the network structure, we define the in degree and out degree for a user. So in degree is the number of people that follows the user, and out degree is the number of users the user follows, right? So we also make the histogram of the in degree and out degree. Okay, so both are skewed to the right, which is not surprising. One thing that I wanted to bring your attention to, though, is that you look at the scale, you look at the range of the x-axis, and the one for in degree is much bigger than the one for out degree. And so the largest value that you see here is around 800. So that tells me, so basically there are some users, at least one user in the data set, that are followed by more than 800 users. And keep in mind, we are only considering network with the size slightly over 2,000 users. So the in degree plot basically suggests there are some potentially some superstars. There are a lot of people just follow, right? Okay, so these are some preliminary analysis that we have done, and we want to see what kind of research questions that we may want to answer given the data set and given what we have seen from the preliminary analysis of the data. So the first that would come into mind is how about we do some modeling, right? And so really, how do we model this kind of a dynamic posting patterns? There are some unique features from from the data sets or at least some important features, if not unique, that we have seen that need to be taken into consideration. And specifically, there's large variations in the individual activity levels, that are heterogeneous daily posting patterns, and potentially clustered posting pattern as well. And finally, there's the influence from friends in the social networks. So we have to develop a framework that can incorporate all the 4 features we observe into the modeling process, right? And the next question could also be, can we cluster some of the posting patterns into subgroups? So instead of looking at 2,000 trajectories or patterns individually, maybe there are some ways to better summarize the relationship or the patterns that may be in the data. And thirdly, as we mentioned in the previous slide, there's a presence of some superstars, right? So what we want to see, well, can we identify some influential users on the network, right? And in the person being superstar does not really necessarily mean the person has to be highly influenced in terms of how others' activity will be influenced by the person's activity. But nevertheless, the presence of superstars in the data set may indicate there are some highly influential users. If yes, can we identify those? And based on what criteria are we going to do so, right? So these are the questions that would come into mind as to the things we may want to look into. So what kind of modeling framework are we going to use to answer these questions? Well, we're going to view each user's posting times as a realization from a temporal point process. And to answer the questions, we're going to develop a so-called group network Hawks process, which we're going to explain in the next few slides. Okay, so what we're going to do is we're going to view each individual person's posting patterns as a temporal point process, as a specific univariate temporal point process. But there are multiple users, so we need to treat them, and we're interested in studying their relationship between them, right? So we will eventually treat them as multivariate point processes. But just to start, we're going to look at the univariate point process variant, specifically look at the Hawks process. So what does the univariate Hawks process looks like? So let's say consider some event times, T1, T2 until T little n, in an interval from 0 and capital T. And we're going to use HT to represent, and this is the event history before T. So basically it contains all the timestamps before time of interest, which is T. So for point processes, a very commonly used function to categorize the distribution of the process is the so-called conditional intensity function. For Hawks process, the conditional intensity function takes the following form. So lambda T conditional on the history before T can be written as the sum of 2 components. The first one is mu, which is a constant, and this is called a baseline intensity. So which has nothing to do with the history. And the second component is really looking for all the events before T. So we look at all the event history. And then we calculate the distance between the event and the point of interest. And the function f is called a triggering function. And the function f is typically non-negative. So basically look at the history, and for every observed event in the past, we apply this f function as a function of the distance between that particular event and the given time of interest, which is t. Okay. So commonly used the parametric form for f for the triggering function could be exponential. Okay. So beta is a parameter, and then omega is another parameter in the triggering function. So what does it look like graphically? Okay, so here T1 until T9, these are 9 observed event locations. So when you think about the conditional intensity function, the conditional intensity function can be defined at any given T within this time range from 0 to capital T. Okay, so it's going to start before the first event showed up. It's going to start with the intensity lambda 0. Lambda 0 basically is the mu, which is my baseline intensity function. Once the first event took place, okay, so before the first event took place, you only have the baseline component. Once there's an event that took place, then there is going to be a jump caused by the triggering function. So there is going to be a jump here, okay, and the conditional intensity added this new components, which is T minus T1. And then as T increases, if you think of this as an exponential function, right? So the distance between T and T1 will increases with T. And so you would see this function, the conditional intensity function, will start decreasing until it has another event that took place. Okay, and the second event is going to jump again. Okay, because now you look at the event history, the second event also comes into the summation. Okay, so because of the triggering function, will capture the impact of the second event, and therefore you would see another jump at the second event location. And as time goes, again, it's going to decay. But once the third event happens, it's going to jump again. Okay, so you're going to see this kind of a jumping pattern when you look at the conditional intensity of a Hawkes process. A Hawkes process is called a self-exciting, is known as self-exciting process. By saying self-exciting is really refers to the fact that the event, once the event takes place, is going to really increase the likelihood, increase the value of the conditional intensity function, and as such, it's going to increase the chance for a new event to happen in the following periods after this event. Okay, so this is for a univariate Hawkes process. So in our example, each user, we can think that as a univariate Hawkes process, right? Or univariate point process. A univariate Hawkes process may be appropriate or may not be. But there are over 2,000 users. And as you put them together, they're not going to be independent with each other. Then it's better to view them as a multivariate point process, right? Then the natural question would be, what about the multivariate Hawkes process? What would it be looking like? So what you see here is the conditional intensity for a general multivariate Hawkes process. So I corresponding to the ith user or the ith process. It's conditional on HT here. HT corresponding to this is the event history. Okay, the events history, again, the events history including not just the user i's event history, but also all the other users in the network. So it similarly has baseline components, so mu I. So mu I will be different from user to user. And then this is the part involving a new triggering function, zeta. Right? Zeta now is zeta ij, because the influence is not just coming from the user's own events history, but also for all the users. So zeta ij, apparently there are many different functions, and there are m squared pairs that would come into this expression in terms of the triggering function zeta ij. So one simplified model could be, for example, I'm going to assume a common f function, that's the triggering function part, right? Shared by all the zeta ij functions. Depending on only one parameter gamma. And then there's the theta ij. Theta ij just for a given ij, it's just a fixed number, it's a scalar. So if you look at this model, this is really looks like a very simple model, or at least a very simplified one. But even so, you would see theta ij, there are m squared parameters. And then you have gamma involved as well, right? So if you think about the network, the size of the network increases, And then the number of parameter will increase in the rate of m squared. So potentially this can be a problem, especially think our data set. We only have like 15 days of data, right? Using 15 days of data to estimate 2,000 squared number of parameters, that sounds just a little bit too difficult. So what people typically do is to introduce some kind of a sparsity structure and to force some theta ij's to be equal to 0. And that actually also has very nice interpretations. So what really it says here is if you have theta ij equal to 0, that tells you the jth user's behavior doesn't really have anything to do with the ith user's behavior. So there's no connection between. So user j does not affect user I as long as theta ij is equal to 0, right? So basically by doing this kind of analysis, we can recover some kind of latent network structure to try to see how the different users are connected with each other. So there has been some theoretical investigations, especially when M is diverging. But the work is not really, there's not really so that much work on this regard. This is one way of looking at the multivariate Hawkes process. The other way to look at the multi-network or Hawkes process, so the first one we're looking at here is identify the latent network structure. The network structure is not observed. But what we are dealing with here in the social media applications is that we know the social network structure. So instead of trying to estimate the network structure, what we really need to do is to utilize the network structure and take that into consideration when we do the modeling. So this is really a different line of research. So on this regard, there are some work in the machine learning literature, as I've seen. There are more and more work in the statistical literature. One relevant paper we saw was published by Fox et al. In 2016. So where they consider there is email network structure, and they want to see a users when the pattern of sending out emails, how that was affected by the other users' behaviors in the network. So what they considered is something like a very simple model like the one that you see on the slide. So zeta ijt here is equal to theta I. So we're looking at the ith user. So this is a constant, does not really change with the j. And aij. So aij again is something from the adjacency matrix. So if j follows I, then I follows j, and then aij is going to be equal to 1. If they're not connected, then aij is equal to 0. So aij is something already known and derived from the network structure. And then you have a gamma I, and then you have the remaining part, the exponential part. Right? So by having this kind of a model, you can see the number of parameters dropped from order of n squared to order n. So this is this is a significant reduction. But there are a number of issues with using a model like this. One of them is in the paper that I mentioned. So they basically just consider application. There's no theoretical investigation as to study of the properties of the model. And second, as you can see, theta I and gamma I, they both only depends on I, the user specific. But they don't have anything to do with the users, the jth user, which they are connected or follow, right? So that may or may not be reasonable in a practical setting. Right? So there are issues. That's the point I'm trying to make here. So nevertheless, what we see on the slide is there are two lines of research. One is to identify the latent network structure, and the other one is to use the observed network structure in the modeling analysis. So ours model is based on the second approach. So in the second settings. So what we would like to introduce here is a group network Hawkes process. So think about it, we have 4 users, okay? And let's say there are two groups. We put them into two groups. So the first two users are in one group, and the second users are in a second group. So by being in the same group, we hope their behavior or activity patterns will be similar in a way, right? So of course, we don't get to observe what group they are in, but we assume they are, let's say, capital G groups in a more general setting, right? So for the ith user, there's index GI. GI could be from 1 to capital G, and this is the group membership of the ith user. Okay, so the assumption we're making here is within each group, the nodes are assumed to behave in a very similar way, and as such, we assume to share the same set of group level parameters. Okay, so given this assumption, what does our model look like? Well, since we are considering multivariate Hawkes process, so we're considering for each user I, there is an intensity function for the given user. Okay, so this has conditional intensity, has three components. I apologize. I have to let my son in. He's coming home. Sorry. I apologize. So my son just came back, I locked the door. So anyway, so there are three components in the model. And the first one, just like before, there is the baseline intensity. And so there's the sub-index. Instead of using I, now we're using GI. GI is the group the ith user is in. Okay. The second component in the conditional intensity function, and if you look at the expression, it's summation. So this is TIK less than T. So TIK less than T means we are looking at the events from the ith process, which is the same process from user I, and look at the events before the time point T. Okay. And then there's the triggering function that we need to define. Okay. The third component, on the other hand, and you can see this is J from 1 to M. So we're looking at all the users. Okay. And if you look further inside, you would see the TJL less than T. So we're looking at the jth process, and we're looking at all the events from the jth process that occurred before time point T. Okay. So since here's J from 1 to M, you may say, okay, you're looking at the ith process also, because J can't be equal to I, right? But you have to keep in mind that Aij will be equal to 0 if I is equal to J. Okay, this is the diagonal elements of the Jason matrix are equal to 0. Okay, so as a result, what we are doing here is there is a baseline intensity, and this is the influence from the same user's past events, and this is the influence from the friends that he follows, the user that he follows, and not including him or herself, right? Only the people that he follows from the past, their past events patterns. So going further inside the definitions, and we would emphasize that the baseline intensity function, we're going to allow that to take a periodical form, because as we observe, there are daily patterns in our data set. The triggering function depends on some parameters, and depending on you look at the events from himself, or you look at the events, the impact of events from his friends, these parameters will be different. And we look at the third component, which we call as the network intensity, and you would see the network intensity explicitly uses network structure information Aij. So Aij is characterize the network structure. So the parameter phi, gi, and gj simply specify the group connection string. So instead of looking at a user impacting user, we are looking at group impacting group. Users from one group, how do they impact the behavior users from the other group? And the di here is the outer degree and is used to prevent the inflation of the network. So because the number of users that a user can follow can increases go to infinity, potentially making the network component to be getting to be too big. So by adjusting that, dividing that by di, we already account for that. So the parameters in the model are the group level parameters. So we have beta, gamma, eta, and phi. And the other set of parameter is going to be the G's, the group membership. This is all the group structure is unknown, and we need to estimate that as well. Okay, so to further understand properties of the model and also for the estimation as well, and we need to we would like to introduce the branching structure of Hawkes processes. We started with the univariate Hawkes process. So the branching structure is basically another way to look at the same process. So with the definition of the process is through the conditional intensity. But the branching structure just simply gives us a different view to look at the problem. Okay, so recall the intensity function, the conditional intensity function for univariate process can be written as the sum of two components. So mu will leads to, so basically what we do here is to classify the events that you observed. So these are the observed events. We can classify them into two different types. One is because of the so-called baseline process, which is essentially a Poisson process with a rate equal to the baseline intensity in the definition of the conditional intensity function. And the other process is called the so-called offspring process. The offspring process simply corresponding to events triggered by the preceding events, okay? And through the use of the triggering function that we used in the definition of the intensity function. And in the baseline process, we can also call them as a baseline, as a parent process. And the events, we can call them as parent events. And the events in the offspring process, we can call them as offspring events. So this is what happens in the univariate Hawkes process. If you think of our proposed group network Hawkes process, we can try to have some similar branching structures, okay? But it can be much more complicated. And to be simple, we can consider a setting where there are only two nodes in the network structure. And furthermore, we assume the first node follows the second node, but the second node does not follow the first node. Okay, so for each of the nodes, we have some observed event locations. And because the second node does not have anything to do with any other nodes in the network, which is only node 1 in this example. So what you see here in the for the second node, simply just what you would expect to see from a univariate Hawkes process. So there's nothing very similar to what we see on the first graph. For the first node, on the other hand, you're going to see the blue circles you see in the plot. These are events generated by the baseline process. Okay, and then you would see the purple events. The purple events is generated by an observed event of the process. Okay. And the purple event can further generate another purple event. Okay, so we use the color purple to represent it. This is event generated by a preceding event from the process. Okay, and then you would also see the impact of node 2. So let's say there's a node 2, there's an event from node 2. And this event can generate an event for node 2, but also can generate event for node 1 because node 2's behavior impact node 1's activity, right? So you would see node 1, you're going to have a combination. There's 3 different types of events, and parent events generated by from the process itself, and also events by due to impact of another node, which is node 2 for this example. Okay, so given this branching structure, what we can do is to define to obtain a so-called network transition matrix. So recall this is our definition of the conditional intensity function. So the so-called network transition matrix is simply a matrix that depends on the parameters, some of the parameters in the conditional intensity function. To be more specific, is beta gi, and also the phi gi gj, and aij and di, they are observed. They are not really parameters. Okay. So what is the use of this network transition matrix? Well, it can be used to categorize the network interactions. Okay. And to be more specific, what I really mean here, okay, so one of the things we may want to see is if you think of an event from a user I, let's say, and to be more specific, looking at a parent event, you may wonder, well, how this parent event will impact the events observed in the network, on the network, right? And you could think about it, for example, you could think about it, well, if I look at the impact of a user I, a parent event from user I want to see how many events that it can generate for among all the events of node J. Okay, so if you I guess I should move back. So what we using here is we're looking at the number of events occurring at a subset of network nodes. So S is a subset from first node until all the nodes we have in on the network. And we look at the subset of the number of events occurring on the subset of network nodes that are direct or indirect offspring of a parent event originating from the ith node. Okay, if you look at the expected value of the number of events, that can be written in a form that depends on the network transition matrix that we defined in the previous slide. Okay. So in this expression, we have the EI corresponding to EI is basically is you take the value equal to 1 at the ith element entry, and everything else is equal to 0. And then ES on the other hand, take a vector, it's a vector with 1 for entries whose indices are in S and 0 elsewhere. Okay, so in the next slide, basically we look at it. So S can be any subset of the network nodes, right? So in the next slide, I basically look at it, well, what if you look at the subset to be just one node? And what if you look at the subset to be all the nodes? What if you look at the subset to be all of the nodes belongs to a particular group, let's say the G prime group. And by looking at by setting the S to take different forms, we can categorize using the network transition matrix, we can categorize the node to node influence, node to network influence, and also we can have the group to group influence. And we have the word dynamic is really, we are also accounting for, the behavior, the baseline pattern. The baseline pattern is not a constant. It's a change from with time. So this is the baseline. This is the network transition matrix. Okay. So what I would like to talk very briefly next is to look at the estimation. So this slide is basically we are defining the baseline intensity function, and we are using spline approximation, and we are making this function to be a periodical function, so as to model the daily pattern we observe in the data. Okay. So given the definition of the conditional intensity function, so and the first part again, this corresponding to we are estimating the baseline intensity using splines. Okay. So given this expression, we can write out the joint likelihood, and therefore we can estimate the parameter by using MLE. But the problem is the optimization is going to be quite a challenging here. Okay, so the maximum likelihood is not convex, and it's difficult to maximize. So what we did is instead to use EM algorithm. So I just want to briefly talk about the idea without going into the details. Okay. So what we did here is to introduce a latent random variable ZIK. And so we are looking at the event TIK, which is the kth event from the ith user. Okay. So for this event, we have a latent random variable ZIK associated with it, and ZIK is equal to J and L. Okay. So what does this really mean? So if J and L equal to 0, and then we say TIK, this particular event, is a parent event. Otherwise, the TIK, this particular event, is triggered by the event TJL. TJL is the Lth event at the Jth node. Okay, so by given this definition, so we can separate by looking at the value of JL, and we can have three different components. One is indeed ZIK equal to 0, 0. So that's basically we are looking at parent events. And the other one is we have ZIK equal to IL, right? So basically you are looking at a TIK and influenced by TIL. So you're looking at events from the same process. They are both from the ith process. And the last one is ZIK equal to JL, and the J is not equal to I. So in this setting, you are considering events generated by a different process, from a different process. Okay, so we are looking at these three different situations. One is the parent process, and then events by previous events of the same user, and then events generated by a different user. And given this information, each one of them, we're going to look at a series of events, follow that satisfy any of the given conditions, situations, and then we can write up the likelihood for that single series of events. And so that's based on the condition that we know the value of the latent random variable ZIK. But in reality, we do not know that, right? But given we know that, we can write out the complete data log likelihood. And if we, so these are the likelihood that we're going to see here. But in reality, we don't know that, right? So instead, we're going to treat that as missing data and then use the algorithm to estimate the parameters. So I think I'm going to skip the next few slides and jump into the application right away. So, okay, so what you see here is the estimated baseline intensity. And recall that we not only need to, we also need to do the obtain the subgroups. So for our example, we obtained 4 subgroups, and for each one of them, we can estimate the intensity functions, the baseline. So this is the baseline intensity functions, which I set as a background intensity functions here. Okay, so these are the 4 different groups, and the third group, this is the public news, as you can see, is much more active than the other groups. And they're the one like called the regular users. This is the group that has the smallest the baseline intensity functions. Okay. So the next slide, what we see here is all the estimated group level parameters. And recall, this is the definition of our conditional intensity function. So what we just did is estimate mu gi in the previous slide. And what you're seeing here is the beta, eta, you have the phi, which is a matrix, and then there's also the gamma, right? In the trigonometric function, we use the exponential form. So this is the what you see in the two summations here. Okay. So how do we interpret these results? Well, firstly, you can see the first group, the regular users, has the highest percentage, over half, slightly over half. So for beta G, and you can see beta G is the larger value implies bigger impacts of one's own past event. So this is really occurring the second component here. Okay. So eta, on the other hand, a larger value implies shorter impact, or maybe larger value, I would say, or smaller impact from one's own past events. Okay, and what you can see here is the third group. The public news, it has smallest beta value, eta value, and that simply means this is the one that has the longest dependence range of all the four different groups. So gamma G, on the other hand, is trying to capture impact of others, groups from on members, others on the user. And so a larger value implies, again, a smaller impact from other groups. And for the third group, again, we have this value to be very large. Actually, I think this is not converging here for this value. So what this tells me is this group is very much unaffected by the behavior of activities in other groups or others. Okay, the phi matrix tells us really the impact stream of group G prime on group G. Okay, so this is the impact of the first group, users in the first group on users in other groups. And this is really the second, the users in the second group and impacting users in other groups. Okay. And this is the third, and this is the fourth. I think you can see this value is large. That simply say the second group has large influence on the behavior of the fourth group. Okay, so the next slide that we see here is we did the influential user analysis, so what we see here are the top 20 users that has the most influential power, and we can see every single one of them, either from the second group or the third group. Okay. We also look at the top 100 influential users, and the vast majority actually still from the second and third group. And the remaining four figures simply gives us the influence curves of the different users from the different groups. And you can see the one from the third group, the public news group, actually has the largest impact on. So this is so what you see here. This is the impact on the other three. Each of the curve represent the impact of the public news on users in one of the other remaining three groups. So regular users, opinion leaders, and active users. Okay. So you can see that the public news has the most impact on the other groups. And the first group, on the other hand, has very little impact. And similarly so for the active users. For the opinion users, you would see it has relatively high impact on regular users and active users, but it has almost no impact on the public news users. Okay, I guess I guess I'm gonna I should stop here. I see only there are 5 minutes left. So I'd be happy to take any questions that anyone may have.
Does anybody have any questions for Dr. Guan?
I do have a question.
Hi.
Hi, Dr. Guan. Very nice talk. Very interesting.
Thank you.
So I'm wondering about that baseline intensity function, the mu, and whether there might be any scenarios in which there could be, where it could be difficult to distinguish between that baseline and the triggering function.
Mm-hmm.
Or it should always be well identified. I'm just wondering if there are any situations where it could be difficult to distinguish between the two.
I think these two, there's really not much issue. I think these two can be distinguished.
Okay, yeah, I was just wondering if there were any specific scenarios, or for example, if you were to make that mu, well, in your case, you tried spline, right? In the example.
Yeah.
Mm-hmm. Yeah, no, that was all. I just was wondering if there were any situations.
And this one, it's really not that much issue here, because we really have the mu's you repeat over days. It's not just one. It's not like there's no replications. For the mu, the baseline intensity, there are replications, because the pattern, as you recall from the very beginning. So I'm going to go back. Sorry, scroll back. This function actually keep repeating itself.
Mm-hmm. Mm-hmm.
So for our example, our analysis, we didn't really encounter any problems. I think partially it could be because of that, but because otherwise you can't just impose a very flexible spline, approximation for the baseline intensity function. That could be certainly be an issue.
Yeah. Okay. Thank you.
I don't actually think you can do that. That's probably going to be cause the problem that you should mention it. If you want to make it very flexible, it's simply not going to happen. If you have covariates, that's a different thing. You can try to put it into cover that. But you just do a spline approximation without replicates throughout the entire time domain, that's going to be an issue.
Okay, thank you. Very nice talk.
Yeah, thanks.
I also have another question if nobody else has any other questions, which is, so given that you've used the EM algorithm to, if I understand correctly, you used it to really distinguish between the parents and the immigrants, the parents and the offsprings, right?
Yeah.
So that way, at the end of the day, you have an estimate. You can then classify them, right? Because I've seen that with Hawk's processes, sometimes you can estimate them in a way that at the end you have you estimate the parameters of the conditional intensity function, but not necessarily, you can't necessarily distinguish between the parents and the offsprings. But in this case, you can, right? Am I correct?
When you say distinguish, what do you mean? For a given event? For a given event, you can't do that, right? There's no way to see if it's parent or not parent. You can only have the likelihood, the probability for it to be one of the three cases.
Oh, okay, yeah, but you do get the probability, right?
Yes,
you get a probability. Okay.
Yes, yes, we only get the probabilities. Yeah.
Okay, yeah, thank you.
This is really just like the labeling that the random variable that we introduce is to try to transform this into a missing data problem. So the labels, are missing. Once we know the labels, then we can write out the complete likelihood, because each one of the parent event from this motivated or generated by the same process or by network processes, right? So there are going to be each one of them. You take them out, you can treat them as a Poisson process. You can write out the likelihood function. So
Right.
that's based on the assumption you know the value of Zi and K. But in practice, you don't know it, then you need to calculate what is the probability of Zik equal to 0, parent event, or any JL. So these are the probability that I mentioned we can calculate, but we can never know that either is a parent or otherwise.
Mm-hmm. Yeah. Okay. Thank you. Very nice.
Thanks.
Dr. Guan, there is a question in the chat. Somebody was asking about whether or not a list of references might be available for your talk.
I don't have, but I think I believe the paper is on the web. You can search for it.
Okay.
I think the name of the paper is called Group Network Hawks Process.
Okay, great. Thank you.
Yeah.
We're just after 2. Maybe I don't know if we need to wrap up or if you have a couple more minutes in case there's a question. Doesn't seem like there's any other questions.
Marcy. Hi, Marcy. If I can just say thank you for Yongtao for nice talk, and thank you for giving this seminar.
It's my pleasure. Thank you very much. Thanks,
Yes.
everybody.
Thank you, Dr. Vidakovic.
Yeah. Thanks, Marcy.
Thank everybody for joining us today. It was a very interesting talk. We learned some, at least for me, I learned some new things. So I appreciate Dr. Guan taking his time to share with all of the students from Texas A&M University, former and present. We continue to have these webinars. We try to have them on a monthly basis. I think we don't have another one scheduled till February, but we have February, March, and April scheduled. So keep your eyes open for these announcements. And everybody have a happy holidays.
Thank you. Thank you, everybody.
Thank you. Take care.